Yeah. Good evening to all the participants of this NPTEL course. So, we will start today's live interaction session. Presently, as you might be aware, we are in week 10 of this live session, and we are going to be solving some sample problems on the uh, behavior of columns under axial load and biaxial, uniaxial, and biaxial bending. So, let us start with the session. I'm going to turn off the uh, video and I'm going to start uh, sharing my screen. Okay. Yes. I welcome you all to this NPTEL course, Advanced Infos Concrete Design. And the course instructor is Professor Surya Prakash from IIT Hyderabad. And presently, we are in week 10 of this live session. So, uh, this is a 12 weeks course, and we have looked into various aspects of uh, reinforced concrete design in the previous 9 sessions. So, uh, I think, yeah, I believe after this session, there will be another 2 sessions. Uh, so, let's proceed with the session. This session is presented by me. My name is S. Lalit Sagar. I'm a doctoral candidate and PMR fellow in the Department of Civil and Environmental Engineering at IIT Delhi, and I welcome you all once again. This will be today's agenda. As always, we are going to be solving some sample problems on the following topics. So, in week 9, we started with the design of columns. So, we are going to take up uh, module 8 in that parts 3, 4, and 5. So, in module 8.3, as you might have already seen in this week's lecture, so we dealt with the behavior and analysis of the short columns under axial compression. So, short columns or slender columns, it's going to be determined based on the slenderness ratio. So, IS 456, it prescribes a certain threshold. So if the slenderness ratio is below a certain limit, it might be classified as a short column, or else it is classified as a slender column. Okay. Uh, under module 8.3, we studied the effect of load eccentricity on the column behavior, because in modules 8.1 and 8.2, we essentially studied the behavior of columns under pure axial loads, right? So in this module, we are considering the effect of the bending moment that is acting on the column, how that influences the stress distribution in the column, and how do we perform the analysis and design the column accordingly, right? So uh, another aspect is that we developed the PM interaction curve. So that is when a column is subjected to simultaneous axial and bending loads. So, what is the beam interaction curve look like, and what are some of the salient points of the PM interaction curve, and how do we construct such PM interaction curve for any given column cross section, right? And in module 8.4, we considered the behavior and design of short columns under axial load and biaxial bending. So what happens when there is bending along both the axes, the cross section of the column? Okay. So in this week's lecture, we looked into the PMXMY interaction diagrams of the columns, which are subjected to biaxial bending, and what are the IS code provisions for reinforcement detailing. And then we looked into the IS code procedure for the design of columns under the biaxial bending. And in module 8.5, we considered the behavior and design of reinforced concrete slender columns. So when we are analyzing uh, and designing a reinforced concrete slender column, so how the procedure is different of a slender column when compared to a short column. Okay, so basically we understood the behavior, and then depending on the codal provisions, we tried to look into the design aspects for such slender columns. Okay. So with that, I think we can proceed to the sample problems now, right? So first we are starting with the conceptual problem. So excuse me. So the first question is, in the PM interaction curve that is shown below, what does the point P represent? Okay, so there are 4 points. So what does the point P correspond to? Okay, that's the question. So there are four options. First is pure compression, second is pure moment, third is that is option C is decompression point, and option D is balanced failure. Okay, so basically each of these points corresponds to one description among the options given below. So let us see the answer now. So the point B corresponds to the decompression point. Okay, that is option C. Okay, so let us look at the explanation. So this picture has been taken from the lecture slide. So here we can see the PM interaction curve, that is for any given cross section. So what will be the axial capacity and what will be the moment capacity, right? So this is the, you can say it is an envelope, and if the axial load and the bending moment combination, if that falls within this PM interaction curve, then it is considered to be safe. But if it is falling outside this curve, then uh, it undergoes failure. Okay, that is the meaning of this PM interaction curve. And here, point B represents a decompression point. That is to say that when any point within this PM interaction curve lies between these region A, 0B. So whenever it lies within this region A, 0B, A, okay, so there is the entire cross section is essentially subjected to compressive stresses. So, but the moment it falls outside this region, a part of the cross section goes into the experiences the tensile stresses. Okay, that is the meaning of this decompression point. That is beyond point B, that is towards point C and D. A part of the cross section slowly experiences the tensile stresses. Okay, that is the meaning of this. So here, point B basically corresponds to the decompression. Moving forward, yeah, so we are going to start a numerical example now. So for the column cross section that is shown below, it is intended to derive and plot the PM interaction curve. So we are going to be, plotting a PM interaction curve for a given cross section, right? As we can seen as we saw in question 1. So question 2 is to determine the capacity of the column under pure compression as per IS 456 2000. Okay, so let us start with the numerical problem now. Okay, let me just take the, the, the pen. Okay, so so maybe we can very well assume that it is a short column, right? And how do we find out the actual compression ratio, actual compression capacity? Okay, so how do we find out the capacity of the column under pure compression? So we have Pu is equal to as per clause 39.3. We have Pu is equal to 0.4 FCK into AC plus 0.67 Fy into AAC, right? So this can be written in turn as 0.4 FCK into Ag, where Ag is the gross cross-section area, plus 0.67 Fy minus 0.4 FCK into ASC. Right? ASC is the steel in compression. So now let us look at the different parameters of the cross section. Right. So we have the cross section that is 450 by 450 millimeter, and the effective cover is 60 millimeter, and it is reinforced with 4 bars of 25 mm diameter. Right. And FCK is 30 MPa and Fy is 500. Okay. Let us write down that data in the next slide. Okay. FCK is 30 MPa and Fy is 500 MPa. And what about the cross-sectional area? We have Ag is equal to 450 square, that is 202500, 202 mm square, and ASC is pi by 4 of 25 square multiplied by 4 bars, that is 1963.5 mm square. Okay, let us plug all these values in this particular equation and try to find out the actual capacity. Okay, so Pu is equal to 0.4 into 30 into 202500 plus 0.67 into 500 minus 0.4 into 30 multiplied by 1963.5. Okay, and we need to convert this from Newton to kilonewton. So I'm getting a value of 3064 kilonewton, right? Pu is 3064.2 kilonewton. So if you're happening to watch this, try to confirm that you're getting the same answers. So the answer is 3064.2. So that corresponds to option B. Okay, so let us proceed to the next question now. So essentially, we are in question two where we are where we are constructing the PM interaction curve. So we have obtained this point that is corresponds to the pure axial compression, that is point A. Okay, so let us proceed to uh, determine the rest of the points and try to construct the PM interaction curve. So now the third question is for the column cross section given in question 2, determine the pure moment capacity as per IS 456 2000. Okay, and the effective cover is 60 mm. So what we need to find out is that the pure moment capacity, okay, that is given by point D. Okay, so point D in this PM interaction curve corresponds to the pure moment capacity. So let us proceed to find out that one. Okay, so excellent. I think we are having the figures also here. So let me draw the cross section. Okay, then we can take the help of the Excel sheet in order to determine the moment capacity. Okay, so here is the cross section. So we have considered a square cross section of dimensions 450 by 450 millimeter. It is reinforced with 4 rebars of 25 mm diameter. So we have 450 by 450, and the effective cover is 60 millimeter along all the sides. 60 millimeter. Okay. Okay. This is not required as of now. I mean to say the bottom side effective cover. Okay. So what we need to do here is basically carry out a flexural analysis of this cross section, right? So let me draw the neutral axis. Neutral axis. Okay. And okay. So this is represented by X. Okay, and the effective depth, right? Effective depth is 450 minus 60, that is 390 millimeter. Okay, so this depth below the neutral axis up to the center of the rebar, that is given by 390 minus x. Okay, and let me draw the strain distribution and stress distribution now. Take a different color. Okay, this will be 0.0035. Okay, and we'll draw the stress distribution as well. And please note that this is a doubly reinforced cross section. So in addition to the compressive force due to the concrete block, we need to consider the compressive force due to the steel rebars as well. Okay. So let us go to the Excel sheet in order to solve this problem, right? Yeah. So we have here. So basically, what we need to do here is enter the dimensions of the cross section. So it is having a width of 450, depth of overall depth of 450 mm, and the effective depth is 450 minus 60, that is 390. And AST here, AST is given by, so it is half of the 1963, right? So AST is basically, let me write it here. AST is pi by 4 of 25 square multiplied by 2, which gives me 981.981.75. Okay, so then we need to, it automatically gives the percentage of the tensile reinforcement, and AAC is same, even that is 981.75, and it will automatically calculate the percentage of steel reinforcement in the tension zone and the compression zone, and D prime 60 millimeter, and the grade of concrete FCK is 30 MPa, and then we are considering uh, the ultimate strain of concrete as 0.0035, and the grade of steel is 500 MPa, and we are not considering any axial load. Okay, so we need to determine the depth of the neutral axis by a trial and error method, so that the tensile strength from the rebars in the tensile region should be equal to the sum of the compressive forces due to the compressive stress block of concrete and the compressive force in the reinforcement in the compressive region. Okay, so I have already entered this value. So basically it is obtained from a trial and error. So basically, if the overall effective depth is 390, we start from a value of d by 2, that is almost 195, right? We start with a value of 195, and then we perform a trial and error until both these, uh, the tensile force and the compressive force balances out. Okay, so we can just play around with different values, and ultimately, for a value of 69.15, we're able to balance both the tensile force and the compressive force. Okay, I'm not going into the depth of this because we have already dealt with in the analysis and design of flexural members, so you may please refer to that. And then ultimately here we have already, the moment is already given, so just for for practice or for revision sake, let us proceed and determine the moment capacity anyhow. Okay, so what we can do is we can consider the uh, we can take the moment about the tensile reinforcement. Okay, and then we can write down the equation for the moment capacity. So M is given by Cc into D minus 0.42 XU plus Cs into D minus D prime. Okay, so let me write down what is the value of each of these terms, right? Cc is the compressive force in concrete, right? So that is 336 point, yeah, let me write 336 kilonewton, right? 336 kilonewton, right? And we have Cs is the compressive force in the steel reinforcement in the compression region. So that is 90.93. So 90.9 kilonewton. Okay. And D we know that is 390 mm, and XU is 69.15, as we have already determined, and then D prime is 60 millimeter. Okay, so we can plug all these values and see what is the moment capacity that we get. 336 into 10 to the power 3, converting it in terms of Newton and millimeter. D 390 minus 0.42 into 69.15 plus Cs is 90.9 into 10 to the power 3 multiplied by 390 minus 30. 390 minus 60. Okay, so solving that, let me write it here in a different color. I'm getting a value of 151.3 kilonewton meter. Okay, so I request the participants who are watching it and the recording to kindly verify this value and check that the calculation is correct. So the pure moment capacity of the column is option C, 151 kilonewton meter. Okay, so we have obtained 2 points out of the PM interaction curve. We have obtained the point corresponding to pure compressive load and the pure moment. Okay, now let us proceed to obtain the remaining 2 points. Okay, so for the cross section given in question 2, determine the actual compression and moment capacities corresponding to the decompression point as per IS code. Okay, so decompression point is point B, as I already mentioned. That is the last point when all the fibers of the column are in compression. Okay, and none of it is under tensile stresses. Okay, so do we have the sketch here? Okay, let me draw it. You know, draw the sketch. Okay, and this will be the strain distribution. So decompression point is the point when the entire cross section is in compression, right? So as we can see here, the bottommost fiber, it experiences zero stresses. Okay, right. So this corresponds to the strain in the reinforcing steel, epsilon SC1 and epsilon SC2, and this would be the stress distribution. Okay, so the entire block is in compression, right? So rectangular, it's a mix of rectangular and parabolic. Okay, and we can consider that the resultant is here, right? CC. Okay, let me write down the dimensions also. So 450 by 450, and this is 2 of 25 dia. And we are going to assume that the peak strain in concrete is 0.0035. Okay, so from this we need to determine the strain in the compressive steel. Okay, from similar triangles, right? Epsilon SC1 is equal to 390 divided by 450 into 0.0035, and epsilon SC2 is 60 divided by 450 multiplied by 0.0035. Okay, so from these strain value we can proceed to find out the stress value, and that is how we can calculate uh, the compression capacity and the moment capacity. Okay, so epsilon SC1 turns out to be 4.67, into 10 to the power minus 4, and epsilon Fc2 turns out to be, okay, I think I basically interchanged the values, right? Let me erase it. So epsilon Sc1 is 3.03, 3.03 into 10 to the power minus 3, right? And epsilon Sc2, right? That is here, that is equal to 4.7 into 10 to the power minus 4. Okay. So once we have the strain value, we need to proceed to find out the stress value. Okay. So that we can obtain from this particular table given in SP16. So this can be taken, you can have a look at it from the notes as well. Okay. So for FE500, we need to uh, look at the strain value, right? And then uh, based on the interpolation of this of the values given in the table, we can proceed to find out the stresses. Okay, so I'm going to write down the values that I got corresponding to these. So 0.00303, so it lies between these two values, that is 413 and 423, right? And I got a value of 421.1 MPa. 421.1 MPa. Okay. And then corresponding to this value, well, this you can obtain directly from multiplying it with the Young's modulus, epsilon Sc2 multiplied by the Young's modulus. That gives me a value of 93.3 MPa. 93.3 MPa, right? So, so how do we find out the value of the compressive force in the stress block? So, okay, let me write down the next page so that everything is in one single page. Okay, so we can write down stress block that is given by 0.36 FCK into P into XU. Okay, that is nothing but 0.36 into FCK is 30 MPa and B is 450, right? And the neutral axis depth is the entire depth of the cross section, that is another 450, right? Multiplied by 1000 to express that in terms of kilonewton. So I'm getting a value of Cc as 2187 kilonewton. 2187 kilonewton, right? So after that, we can proceed to find out the compressive force in the uh, rebars in the bottom region and the top region. Okay, so that's the top is CS1, right? CS1, that is given by the stress into the area. So stress is 421.1 multiplied by 981.75. Okay, and let me write down the compressive force in the bottom steel as well. That is 93.3, if I'm not mistaken. Yeah, 93.3 into 981.75. So this gives me the value of, okay, 413.4, 413.4 kilonewton, and CS2 is 91.6 kilonewton. 91.6 kilonewton. Okay, so we have this. So how do we find out the axial capacity? Axial capacity is nothing but the sum of all these values, that is Cc plus Cs1 plus Cs2. So summing up all these values, I got a value of 2692 kilonewton. 2692 kilonewton. Okay, that is the actual capacity. Okay, so we got the actual capacity. Now let us proceed to find out the moment capacity as well. Okay, so how do we find out the moment capacity? Well, you take the moment of all the forces about the mid height of the section. Okay, so at the mid height, you can just let me take a different color. So is given by M is given by Cc into yeah, D minus XU. Sorry, D by 2 minus XU, right? That is the um, point at which the resultant compressive force from the concrete stress block acts, right? So that is one. And then we need to add the CS1, the moment due to CS1 into uh, D by 2 minus D prime. So D prime is the effective cover. And we need to subtract because if both of these moments, right, contribute to the positive moment, both of these forces contribute to the positive moment, that is Cc and Cs1, right? So here it is Cc, this is Cs1, and this is Cs2, right? Both of them are contributing in the anti-clockwise direction if we take moment about this mid height, but this one contributes in the clockwise direction, right? Red contributes in the clockwise direction. I'll take the red color to highlight that. So these, while you need to add up the moment due to Cc and Cs1, you need to subtract the moment due to Cs2. Okay, minus Cs2, taking moment about the mid height, that is d by 2 minus d prime. Okay, I'll write down all the values so that you can verify this with your calculations later on. 2187 into 10 to the power 3 multiplied by mid height is 225 minus XU is nothing but 0.42 into 0.42 into 450. Okay, plus CS1 is 413.4, yes, into 10 to the power 3 into 225 minus 60. Okay, I'm sorry, I need to adjust it over here. So here we have 91.6 10 to the power 3 multiplied by 225 minus 60. Okay, so we are all set. So from this we can obtain the moment capacity, that is M is equal to 131.8 kilonewton meter. Okay, I request you to just check all the calculations if possible. Okay, and so we can round it off to 132. So correspond to the decompression point, we got the axial load and the moment capacity. Okay, so we have obtained point A, pure axial capacity, point D, pure moment capacity, and point B, that is the point of decompression. Now we need to find out the um point C corresponding to the balanced failure. Okay, So what is the meaning of this balanced failure? So balanced failure means that the peak compressive strain occurs at the same time as the peak tensile strain. Okay, I'll draw the cross section for better clarity. Again, oh, sorry. Okay, here we go. Right. So if we look at the strain profile of the cross section, here 0.0035, this occurs at the same time as the yielding of the tensile reinforcement occurs. Okay, that is epsilon st is 0.00417. So how we are getting this value? Okay, have a look at this table taken from SP16. So this is the the peak strain. Okay, so corresponding to this peak strain, okay, that is FYD, okay, corresponding to the ultimate stress level that we consider for the design purposes, that is 0.87 FY. The peak strain is 0.00417. Okay, so from this we can determine the depth of the neutral axis. Then we can proceed to find out the different forces acting on the cross section. Right. So again we have CC. Then we have oh, this has to be the other way around. Has to be the other way around. That is CS. And then we have the tensile force, that is TS. Right. So how do we find out those values? We need to determine the strain corresponding to these levels as well. That's epsilon SC, and we have already epsilon ST. Right. So from similar triangles, we can easily find out. Right. So this effective depth is 390 millimeter, right? And XU for FE500 is, anybody remembers, it is 0.456 into B, right? So that turns out to be 177.8 millimeter. Okay, so we have, so this depth is 177.8, and this is 390 minus 177.8. Okay, so but I think this is not really required right now. But what is important is we need to find out the strain corresponding to the compression steel. Okay, that is, we have 0.0035 divided by 177.8 is equal to epsilon SC divided by 177.8 minus 60. Remember, the effective cover is 60 millimeter. Okay, 177.8 minus 60. Solving that, we obtain the value of epsilon SC as how much? 2.319 into 10 to the power minus 3. Why do we need this? Because we can, from the strain, we can proceed to find out the stress. and from the stress we get the forces, and then once we um, perform the force equilibrium, we can obtain the axial load, and then we can proceed to determine the moment capacity. Okay, so corresponding to epsilon SC of 2.32 into 10 raised to minus 3, we can obtain the value of FSC, right? So 2.32, it has to uh, lie between these two values, that is 391 and 413, right? So I'm getting value of 393.85. FSC is 393.85 MPa. Okay, so now what we need to do is we have to find out the different forces acting on the cross section, that is CC, CS, and PS. Okay, let us proceed to do that. We have CC is equal to 0.36 FCK into P into XU, that is 0.36 into 30 into 450, and what is the value of XU, that is 177.84. Okay, which gives me a value of 864.3 kilonewton. Okay, so I request the participants also. No participants. Okay, so to check these values, okay, and here we have CS is equal to FSC into ASC. Okay, and then we have sorry, it has to be TS, right? TS is equal to FST into AST, right? So we have FSC is 393.85, 981.75, right? And then we have TS is we can take directly from this, that is 343.8, 3 oh sorry 434.8 into 981.75. Let us write down what are the resultant forces. So here we have 386.7, 386.7 kilonewton, and here we have PS is equal to 426.9 kilonewton, right? 426.9 kilonewton. Okay, that's great. So now let us find out the value of the um, actual capacity corresponding to this point. So what we need to do is we need to add this CC and CS, then subtract the value of TS. Okay, that is CC plus CS minus TS, which gives me a value of 824.1 kilonewton. Okay, 824.1 kilonewton. Okay, then let us proceed to find out the moment capacity. For the moment capacity, we need to consider the mid height of the cross section. Okay, so we have the mid height over here, right? And if we consider the moment capacity, CC is acting in the anticlockwise direction, so is the CS, and TS also acts in the same direction. Okay, so let me write down the value of equation for the moment capacity. M is equal to, right, CC into d by 2 minus 0.42 XU, right, plus CS into d by 2 minus d prime plus we have ts into d by 2 minus d prime, right? So you can just substitute all the values. So here d by 2 is essentially d by 2 is 225 mm, 225 mm, and d prime is 60 mm, right? D prime is 60 mm. Okay. So once we plug all the values and simplify this equation, we get the value of moment capacity M as how much? 264.14. 264.14 kilonewton meter. That is the moment capacity. Okay. So here we have the moment capacity and here we have the axial capacity. So 824 and 264. So option E is the correct response. Okay. So once we have that, okay, let us plot the PM interaction curve for the M30 concrete, right? So the curve that you see here, that is the PM interaction curve for M30 concrete. This is the curve for the M30 concrete, right? And this is what we got from the M40 concrete. Okay, this was the M40 concrete is the example that was taken up in the weekly lecture, and this is the blue curve that we plotted from M30 concrete is the one that we plotted by using the values that we have just calculated in today's live interaction session. Okay. So again, I will just write it down for you. So A corresponds to the pure uh, compression capacity, that is 3064 kilonewton, and then here point D corresponds to the pure flexural capacity that corresponds to a moment of 151 kilonewton meter, and then here point B corresponds to the decompression capacity, right? That is let me write down the value of P and M, right? That is 2692 2692 kilonewton and 131.8 kilonewton meter. And here this is the point C corresponding to the balanced failure of the cross section, and that has actual load of 824 kilonewton, 824 kilonewton, and the moment capacity is 264 kilonewton meter. Okay, so this concept is very important. So I request you to just practice this. So we'll proceed to the next question now. Okay, so after we have constructed the PM interaction curve, okay, now let us proceed to um, uh, a problem where we are going to design this column that's subjected to axial load and biaxial bending. Okay, now let me provide all the data pertaining to this question now. So it is given that a square column has a sides of 400 millimeter and is subjected to a factored axial load of 1300 kilonewton, and the factored moments about the x-axis and the y-axis are 190 kilonewton meter and 110 kilonewton meter. If the column is unsupported over a length of 3.5 meter, determine the area of the reinforcing steel required, taking M25 concrete and Fe415 steel. Okay. Consider the effective cover as 60 millimeter and assume the um, K factor corresponding to the effective length of the column as 0.85. Okay, so I'll draw the cross section and we can start solving the problem now, right? So let us find out the effective length first, right? So L E is equal to K into L U, right? That is the unsupported length, that is 0.85 into 3500. Okay, so what will that going to be? 2975 millimeter, right? 2975 millimeter. Okay, so now LE by B is equal to 2975 divided by 400, which gives me a value of 7.44. Okay, so 7.44, as we can see from clause 25.12, which specifies the criteria for the short column. So LE by B is less than 12. So it may very well be designed as the short column. Okay, so it can be classified as a short column. Okay, moving on. Let us determine the eccentricity of the column, right? Okay, so for the eccentricity, we have, let us find out the minimum eccentricity first, that is as per clause 25.4. Okay, so we have E min, that is minimum eccentricity, should be equal to L, um, L by 500 plus D by 30. That is, L is the unsupported length, that is 3500 divided by 500 plus dimension, that is 400 divided by 30, which gives me a value of how much? 20.3, 20.3 millimeter. While this is the minimum eccentricity that needs to be considered, let us actually find out the applied eccentricity due to the moment. Let us find out the applied eccentricity. Okay. So how do we find that out? Let us first determine the eccentricity along the x-axis. Okay. So for reference, let us take this as the x-axis, and we'll take this as the y-axis. Okay, I'll take a different color to represent the moments along both the directions, right? So this will be my and this will be mx. That is moment about the x-axis and the moment about the y-axis. So ex is given by my divided by p, or rather muy. It should be muy divided by 3, that is 110 into 10 to the power 6 divided by p is 1300 into 10 to the power 3, which gives us a value of 84.6 mm. 84.6 mm. Now let us find out the eccentricity along the y-axis. Okay, along the y-axis, divide mx divided by b. Okay, mx divided by b, that is 190 kilonewton meter divided by 1300 kilonewton, which gives us a value of 146.2 mm. Okay, so since the applied eccentricity are greater than the minimum eccentricity, we can proceed with the applied eccentricity for the design purposes. Okay, so now let us proceed to the actual design procedure of the hull. Okay, I'll take a different ink to distinguish the coming procedure now. Right, so we have, what is the actual load? 1300, right? Okay, so pu is 1300 kilonewton and mux is 190 kilonewton meter and muy is 110 kilonewton meter. So when a column is subjected to this biaxial moment, what do we do? So the first step is we need to determine the equivalent uniaxial moment. Okay, that is m equivalent, let me write it as MUE is equal to 1.15 multiplied by square root of MUX square plus MUY square. You have to pardon my handwriting, right? So when we plug these values 190 and 110, multiply that by this, as per this equation, we get the equivalent uniaxial moment as 252.5 kilonewton meter. Okay, so basically we need to uh, design for this equivalent uniaxial moment and the axial load. So how do we do that? So we have okay, M25 concrete and Fe4. Oh, we'll proceed to the next page here. Next slide here. FCK is 25 MPa and Fy is 415 MPa. Okay, and we know that Pu is equal to 1300 kilonewton, right? And MUE is 252.5 kilonewton meter, that is 252.5 kilonewton meter. So we can actually solve this problem using the help of the charts given in SP16. Okay, so let me write down, along the x-axis we have this PU by FCKBD, and along the y-axis we have PU by FCKBD, and along the x-axis we have MU by FCKBD square. Okay, so let us find out those values. Can be expressed as small letter pu and small letter mu, that is pu by FCKBD, and this is mu is capital Mu divided by FCKBD square. Okay, that is 1300. Express everything in terms of Newton and millimeter, 25 into 400 square, because it's a square column, and here we have 252.5. 252.5 into 10 to the power 6 divided by 25 by 400 cube, which gives me the value of Pu as 0.325 and Mu can be expressed as 0.158. Okay, and here we need to determine the value of d prime by d. Okay, so d prime, as you can see, is the effective cover um, along the perpendicular to the bending axis that is considered. Okay, so if d is the, if this is the bending axis perpendicular to that, what is the effective cover? So that, I believe we have considered that as 60 millimeter, right? Yeah, so it is 60 by, what is the overall depth, that is 400 millimeter, which gives me a value of 0.15. Okay, so whenever this value of d prime by d falls between these values, okay, so basically we have charts corresponding to d prime by d of, let's say, 0.10, 0.15, and zero point 0.2, and so on. So whenever this d prime by d falls between these values, to obtain the accurate um, values, we need to perform the interpolation. Okay, that we are going to see in the next example that we're going to consider. So for the time being, let us proceed to find out the P by FCK from this SP16 chart. Okay, so here it is not very clear. So let me open the PDF file, and there we can, obtain the value of P by FCK, right? So P by FCK corresponding to Pu by FCK BD 0.325, Mu by FCK BD square 0.158. Okay, where do we have? Yeah, right here. Yes, so it is on page number 130 of SP16, right? What are the values? 0.325 and 0.16. So 0.325, it lies somewhere here, and 0.16 is, yeah, so we can get a value of, okay, I think the next one, right? So it lies between the values of 0.14 and 0.16. Okay, so I am assuming a value of 0.15. That is P by FCK is 0.15. Okay, P by FCK, I am considering a value of 0.15. So what will be the percentage of reinforcement? So P corresponds to the percentage of reinforcement, as you can calculate from this particular equation. FCK is 25. So when we multiply 0.158 25, we get the value of P as 3.75%. Okay. Wait a minute. Okay, I think I have taken up a value of 0.145. Okay, so we can consider this value of 0.145. Okay, okay, 0.145. 0.145 by 25, that is 3.625. Okay. So from this value of P, how do we determine the value of A? Okay, let us rearrange the terms in this equation. Okay, so in fact, it is not required to rearrange. AS is equal to P into PD divided by 100. As simple as that. 3.625 multiplied by 400 square divided by 100. So what is the value that we get? Let me calculate. 5800 millimeter square. 5800 mm square. Okay. So this is the area of steel required for this particular axial capacity and the moment. Uh, Actual load demand and the moment demand. Okay. So option D is the correct response. Now let us proceed to the next part of the question. For the column given in question 7, determine the adequacy of the cross section under combined axial loading and biaxial moment. What is the biaxial moment capacity ratio obtained if 12 bars of 25 mm diameter are provided along all four sides? Okay. Is the column safe under biaxial bending? Okay. So this is the expression that I was talking about. We need to determine the adequacy by finding out this biaxial moment capacity ratio. Okay, what is meant by this moment capacity ratio? Let me just explain. So here MUX and MUI are the moment demand about the x-axis and the y-axis, and MUX1 and MUY1 are the uniaxial moment capacity about the x-axis and the y-axis. Okay, and then we have this term alpha n. Alpha n is a function of this uh, value pu by puz. Okay, and then depending on the value of puz, pu by puz, this particular ratio, we can proceed to find out the value of alpha n. Okay, so let us proceed to find out that. So we have, let me perform a part of the calculations over here. That is, we have 12 bars of 25 mm diameter, right? So ASP is equal to pi by 4 into 25 square multiplied by 12. So what is the corresponding cross-sectional area? What is the area that is provided? Okay, let me just calculate that value. Pi by 4 of 25 square multiplied by 12. And remember that these 12 bars are distributed on all four sides of the column. Okay, this gives me a area of 5890 mm square. 5890 mm square. Okay, and what is the p value over here? P is given by rearranging the terms. We have AS by BD into 100. P is equal to AS by BD multiplied by 100. Okay, that is 5890 divided by 400 square multiplied by 100. What is that value? Excuse me. Yeah, so it is 3.68%. Okay, so the amount of steel that is being provided is 3.68%. Now, what is the value of P by FCK? So, why we are doing all this, we will come to that point in a minute. 3.68 divided by 25, which gives me a value of 0.147. Okay, right? So, we have P by FCK of 0.147. Now, let us proceed to find out the value of PU by FCK BD. Okay, we need to find out the value of PU by FCK BD. Okay, I'll take a different color for better contrast over here. Right, we have PU by FCK BD. We already determined it earlier, but nevertheless, let me find out that value once again. That is 1300. Let me confirm that value, right? Yeah, 1300 into 10 to the power 3, right? Yeah, FCK is 25 multiplied by 400 square. So which gives me a value of 0.325. Okay, so now we have the value of P by FCK and PU by FCK BD, and we have the value of D dash by D, that is 0.15. So from this we need to determine the moment capacity. Okay, so from this we need to determine the uniaxial moment capacity for this axial load. Okay, so let me write down the values that we obtained in the previous slide, which is going to help us in solving the rest of the problem. We have d dash by d is equal to 0.15. Do you have the chart also? No. Okay, d dash by d, and then we have pu by fck bd, that is 0.325, right? And we have uh, P by FCK, that is the provided area of the steel reinforcement divided by FCK, that is 0.147, which can be taken as almost 0.15. Okay, now we are having this. Let us find out the value of mu. Okay, that is mux x1. Okay, mux1 uh, is equal to mu y1 is equal to the value that we find out from the SP16 chart divided by FCK into BD square. What is that value? Let us find out. 0.325 and 0.155. Okay, so we have PU is 0.325. So let us locate this 0.15 has to be somewhere in between this, right? 0.325. Okay. So we are getting a value of, you know, yeah, 0 point close to 0.16, right? Yes. So it lies, somewhere between this, um, yeah, 0.1. It lies between the value of 0.15 and 0.17, right? So as a conservative estimate, I'm taking a value of 0.16. So mu by FCK BD square, I'm considering it as 0.16. Let us see what is the consequences of this. What happens if we consider this value? Okay, I just want to reiterate once again that this I am taking it as a conservative value. Okay, so uh, we'll find out the value, that is 0.16 multiplied by FCK is 25 by 400 into 400 square. Let me write down that value. Mux1 is equal to Muy1. What is that value? 16 into 25 into 400 cube. That is 256 kilonewton meter. 256 kilonewton meter. Okay, that is the moment capacity. Okay, so now it has to satisfy this particular equation. Okay, so now we have the value of MUX. MUX is 190. Okay, and we have MUY. MUY is 110. Then we have MUX1 is equal to MUY1, that is given by 256 kilonewton meter. So the only thing that is remaining is alpha n. So alpha n is a function of PU by PUZ, and we know the value of PU, right? 1300 kilonewton. We need to find out the value of PUZ. PUZ is equal to 0.45 FCK into AG plus 0.75 Fy minus 0.45 FCK multiplied by ASC. Okay, so once we plug all the values, okay, I request you to just verify that you're getting the same value. It turns out to be 3567.2 kilonewton. 3567.2 kilonewton. Okay, this will be the value of PUZ. Okay, so we have PU. Let me write down here, right? I'll take a different ink so that you can make out the difference. So we have PU by PUZ is 1300 divided by 3567, which gives me a value of 0.36. So we know that if the value of PU by 0.36, if the value of PU by PUZ lies between the value of 0.2 to 0.8, then we need to interpolate the value of alpha n between 1 to 2 in a linear fashion. So in that way, we get the value of alpha n is 1.27. Alpha n is equal to 1.274. Okay, so now we have the value of alpha n also. Alpha n is equal to 1.274. So when we solve this equation, right? So when I simplify this by plugging all the values of mux, mux1, alpha n, muy1, alpha n, so this corresponding biaxial moment demand to capacity ratio, that turns out to be 0.986. Okay, so after all these calculation, okay, no, I'm sorry, it has to be 1.025. I'm sorry, we will just, I'm going to verify this once again. Okay, 1.025 is greater than 1.0. Okay, so it does not satisfy this, the clause. Okay, so I'm writing it here as clause 39.6 not satisfied. Clause 39.6 not satisfied. Okay, so I'm going to verify this once again. Okay, or I think I may as well, write down the equation over here. Do we have space? No. Okay, we'll manage it here. Mm, okay, so MUX 190 divided by 256 power 1.274 plus 110 divided by 256 power 1.274. So I'm calculating this value once again. 1.025. Okay, so this value of 1.025, it is clearly more than 1, so it is not satisfied, which means that how will we obtain the value of this, the ratio as less than 1? We need to increase the denominator. Okay, that is, we need to increase the moment capacity, right? So the only way is that we have to provide, instead of 25 diameter, 12 bars. Okay, that is 12 of 25 diameter. We need to try 12 bars of 28 diameter. So that is one configuration. There can be multiple configurations in order to increase the cross-sectional area of the reinforcing steel. Okay, so that is the next question actually. So if we are providing this, ultimately the answer is no. The biaxial moment capacity ratio is greater than 1. It is 1.0025. So the column is not safe under the biaxial bending. So we'll proceed to the next question. So in the question number 9, we need to we are providing 12 bars of 28 diameter on all four sides. Then we will check the adequacy of the cross section under the biaxial bending. Okay, so that I'm going to leave it as a assignment. So you can solve the problem, and I'm going to provide the solution also. So that will be 12 bars of 28 diameter, and the procedure is absolutely the same. Only thing is that the numerical is going to the numerical values are going to change a bit, and the answer for this particular question would be, I'm going to write that value. Oh, so it has to be, it is 0.83, right? So I'm going to write the equation over here, so that you can verify the answer later on. That is MUX by MUX1 power alpha n plus MUY divided by MUY1 power alpha n. Okay, we will get that value as 0.83. It is less than 1.0, hence the column is safe. Hence safe. So I'm going to provide these values. Okay, you may kindly ascertain them later on. So MUX and MUY are as it is. MUX is 190. The demand doesn't change. MUY is 110. Okay, and corresponding to this cross section we have MUX1, MUY1. What are these values? I got a value of, okay, so it is, since it is a square cross section, both of them are indeed the same. That comes out to be 312 kilonewton meter. 312 kilonewton meter, and this too shall be 312 kilonewton meter. And the value of alpha n, okay, alpha n would be 1.207. Okay, so you may please verify this later on that you're getting these values. And this biaxial moment capacity ratio, it comes out to be 0.83, hence it is less than 1. So it is the column cross section, it conforms to this clause 39.6, and it is safe under the biaxial bending. Okay, so this is how we solve the problems for a reinforced concrete column. So we need to be very careful while solving uh, the column that is subjected to complex loading conditions such as the biaxial loading. Okay, so we'll proceed to the next question now. So it is given that there is a rectangular braced RC column of dimensions 400 by 500 mm, and it is unsupported over a length of 7.5 meter. If the effective length is 0.85, will the column be designed as a short column or a slender column? Okay, so first we need to find out the effective length, right? So LE is equal to 0.85 multiplied by 7500, which gives me a value of um, okay, that is 6375 millimeter. 6375 mm. Okay, so how do we determine the slenderness ratio? So that is LE by D, right? Or LE by B. So 6375 divided by 500. 6375 divided by 400. Okay, which gives me a value of 12.75 and 15.94. So since both these values are definitely greater than 12, these shall be designed as a slender column. So option B is the correct response. Moving on, yeah. So this definition of short and slender columns can be obtained from clause 25.12 of IS 456. So we are going to design this slender column. Okay. So here is the data. So for the rectangular RC column given in question 10, subjected to a factored axial load of 1500 kilonewton. So I'm going to write down the values here. So PU is 1500 kilonewton, right? And we have the factored moment at the top, that is MUX top and MUY top, and then we have MUX bottom and MUY bottom. Okay, so that is 60 kilonewton meter. This is 40 kilonewton meter, right? And then the the column is bent in double curvature, and the moment at the bottom ends are equal to 50% of the moment acting at the top, that is 30 kilonewton meter and 20 kilonewton meter. Okay, so these are the moments that we have, right? Determine the total factored moment MUX and MUY considering the primary and the additional moments. Okay, so that is the first part of the question, right? So let me draw the deflection profile of the column to show what it means by this double curvature. Okay, so let us consider this column, right? It is supported on rollers on one end and supported by this hinge on the other end. And let us assume that it undergoes this deflection profile where there is sagging at this moment, at this point M1 subjected to actually P, and it is subjected to this hogging moment at the other end. Okay, that is M2 and load P. Okay, so because it is having this curvature at this point and the opposite curvature, and there is point of inflection in between, this is called as the double curvature. On the other hand, if it is having uh, curvature in the same direction, that is, there is no point of inflection, that is called as a single curvature. So depending on this double curvature, the calculation of the primary moment is going to vary depending on uh, the curvature of the column. Okay, so it is given that we can take, so this k is the modification of the correction factor for the uh, secondary moment or the additional moment, and the effective cover may be taken as 60 mm. Okay, yeah, and the dimensions are 400 by 500 millimeter. Okay, so this is the procedure. So first we need to determine the slenderness ratio and classify the column as a short column or a slender column. So we already classified it as a slender column, right? Classified it as a slender column. Then we need to calculate the primary moments. We're going to see that in a while. Then we need to compare the minimum eccentricity based on the geometry of the column then we need to calculate the applied eccentricity and consider the maximum out of those two values. Then we need to calculate the additional moment and find out the total moment. Okay, that is part of this question. So in the next part, I mean the next that is question 12, we are going to determine the equivalent uniaxial moment as we did for the short column, that is 1.15 into square root of mux square plus muy square, and find out the corresponding AST from the SP16 chart, right? Okay, based on the AST that is provided, determine the actual load corresponding to the balanced moment, that is PUPX and PUBY. Okay, from there we can determine the accurate value of the moment factor, that is K. From then we can determine the revised moment and verify the adequacy of the column section using the moment capacity, the biaxial moment capacity ratio. Okay, so we'll proceed one by one in this particular design example. So now let us find out the primary moment. Okay, so the primary moment is given by okay, so we have this mu1 and mu2. Okay, so mu1 is the smaller moment. Okay, mu1 is smaller than mu2, and if the column is in the double curvature, okay, so this mu1 can be negative. Okay, so the primary moment is given by, so what do we call this primary moment, right? Primary moment, I'm going to call it as mux, right? M u2x minus mu1x. Okay, so mu2x minus mu1x, that is, oh, that has to be 0 0.6. We need to consider a factor of these values, right? Right, I'll erase and write it down. 0.6 mu1x. Okay, and this is nothing but 48, 60 and 30, right? 0.6 into 60 minus 0.4 into 30. So mux is 24. Correspondingly, we have MUY, that is the primary moment, is 0.6 MU2Y minus 0.4 MU1Y. So those values are, it was 60 and 30 here, and this is 40 and 20. That is the primary moment MUY is 0.6 into 40, that is 24. 24 minus 8, that is 16 kilonewton meter. Okay, so now let us proceed to find out the the eccentricity, right? So the minimum eccentricity is given by E min is equal to 7500, right? So we need to consider the E min above the x-axis, sorry, along the x-axis, right? That is E min along the x-axis, that is L by 500 plus B by 30, right? That is 7500 divided by 500 plus 400 by 30. So which gives me a value of 28.3. So then we have E min along the y-axis, that is L by 500 plus D by 30. That is again 7500 by 500 plus 500 divided by 30. That gives me a value of 31.67. 31.67 mm. So let me find out now the applied moment. Okay, these are the minimum eccentricity. Let me find out the applied moment, that is MUX. Okay, MUX by PU and MUY divided by PU. That is 24 into e power 6 divided by 1500, right? 16. And this is 10.6 millimeter. Okay, MUY, because it is 16. So out of these two eccentricities, we need to consider the highest eccentricity, right? So we need to consider this MUX, right? MUX, we need to consider this eccentricity. About the y-axis, that is 1500 into 10 to the power 3 into 31.67. Let me calculate that value. 47.5 kilonewton meter. Okay. Okay. After that, we need to find out the value of MUY. So as per the IS code, once we have used the minimum eccentricity for one, you can keep the other one as it is. So we can retain the MUY as 16 kilonewton meter. Okay, there is no need to consider the minimum eccentricity along both the axis. So MUY can be kept as 16 kilonewton meter. So x-axis is the major axis and y-axis is the minor axis. Now we need to proceed to find out the value of MAX and MAY, that is the additional moment. Okay, so MAX and MAY, and we'll take a modification factor K is equal to 0.5. Okay, that we are going to find out the accurate value later on. And whatever this additional moment is there, we need to multiply that by the value of K. Okay, we need to multiply this by the value of K. Okay, so we have mx is equal to K, that is in, okay, I'll start substituting those values straight away, right? That is 0.5 into pu is 1500 10 to the power 3 into d is 500 divided by 2000. Okay, and lex we have, okay, so we can use the Slender's ratio values straight away over here. lex by d, that is given by 12.75. Okay, 12.75. Okay, and other is 15.94 square, and here we have zero point 0.5 into 1500 into 10 to the power 3 into 400 divided by 2000 multiplied by 15.94, right? 15.94 square. Okay, what does this value? This value turns out to be how much? 30.48 kilonewton meter, and this turns out to be 38.1 38.1 kilonewton meter. Okay, so the total moment can be m total x is equal to m t y is equal to mux plus max, right? And here it is muy plus may. Okay, simplifying we have 47.5 plus 30.5, and here we have 16 plus 38, which gives me a value of 78 kilonewton meter, and here it is 30 plus 16, that is 54.1 kilonewton meter. 78 and 54. So option C is the correct response. Moving forward, okay, now we have to determine the area of the longitudinal steel to be provided to resist the axial force and the biaxial moment determined in question 10. Okay, now the procedure is same, right? So we can write the value of mux and muy. These are the total moments, please note. So mux is 78 kilonewton meter and muy is 54.1, right? Yeah, 54.1 kilonewton meter. So the moment, the equivalent moment is me by, I'm going to take it as, instead of 1.15, we are going to take it as 1.2. Again, we are going to take a more conservative value, mux square plus muy square. Solving, we get a value of me as how much? 109 kilonewton meter. Okay, so now from here we find out the value of Pu and Mu, right? That is Pu by FCK BD and Mu or Me divided by FCK BD square. Okay, so for Pu we take the value of Pu as 1500 kilonewton, and here the value of Mu is 109 kilonewton meter. So what do we get here? We get the value of Pu as 0.25 and Mu as 0.046. So what is the value of P that we get? Okay, let us go back to the chart and see. So 0.25 and 0. And let us assume this d dash by d as let us say 60 by 400, that is 0.15. So corresponding to a value of 0.15 and Pu 0.25, 0.05. So 0.25, and here if we consider 0.05, 1, 2, 3, 4, 3, 4, 5. So it is, we can consider that the P by FCK is the minimum value, that is 0.02. Okay. So the reason why we are getting such a low value is because the moment demands are really less for this particular column. Okay. So we can write here P by FCK as 0.02. And what is the value of FCK for this particular problem? The value of FCK is 30 MPa. Okay. So the percentage of steel that needs to be provided, that is 0.02 by 30, that is P is equal to 0.6%. But for a column it is recommended that we provide, it is a good practice to provide 1% of the reinforcement. Let us proceed to find out the value of the cross-sectional area, that is AS is equal to PBD by 100, that is 1 into 400 by 500 divided by 100. So AS is equal to 2000 mm square. So option B here is the correct response. So for this particular slender column, with the moment capacity, with the moment demands as we estimated, that is 78 and 54.1, it is provided that we need to provide 0.6%, but anyway we are going to go ahead and provide a reinforcement of 1%. Okay, so that uh, amounts to 2000 mm square. Moving forward, okay, so for the rectangular column, okay, what is the correct modification factor for the additional moments if 8 bars of 20 mm diameter are being provided? Okay, so now let us see what is the AST that is provided. AST provided, right, that is wait, pi by 4 of 20 square multiplied by 8, right? Okay, let us find out what is the area of field corresponding to that. 2513 mm square, right? That is 2513.3 mm square. So what is the percentage of steel? P is equal to 100 into AST by BD. So that is 100 into 2513.3 by 400 by 500. So that turns out to be 1.257%. 1.257%. Okay, correspondingly, we have P by FCK as how much? P by FCK is, I think, the grade of concrete is 30, right? 0.04. Okay. So what is the value of K? So the K is given by PUZ minus PU divided by PUZ minus PB. So PB corresponds to the balance section. Okay. So let us consider for the moment about the y-axis, right? So we have here P by FCK as 0.04, and here D dash by D is equal to 60 by 400, that is 0.15. Therefore we have PBY is equal to, because D is if D is equal to 400, it is corresponding to the balanced, the actual force corresponding to balanced moment about y axis, right? And then we have P by FCK is equal to 0.04, and uh, yeah, D dash by D is equal to 60 divided by 500, that is 0.12. So from this we find out that PBX. Okay, so how do we find out this PBX and PBY? So here, as we can see, this is the line corresponding to FYD. So we will determine we have, the P by FCK is 0.04. Corresponding to that, we'll find out this particular value of the, uh, the PU by FCKBD and MU by FCKBD square. Okay. So for 0.15, we have PU by FCKBD as 0.12. Okay. So 0.12. Okay. So PU is 0.12. And for D dash by D, PU is 0.14. du dash by d is equal to 0.10. Okay, so corresponding to this d dash by d of 0.12, we need to interpolate the value between 0.12 and 0.14 corresponding to d dash by d of 0.12. So correspondingly, we have this p by v is 0.12 FCK BD is equal to, that is 0.12 into FCK 30 into BD, right? That is 400 by 500, which gives us a value of how much? 720 kilonewton. So corresponding to a balance section, this is the axial load, uh, balanced moment about y. This is the corresponding axial load. Now, the balanced moment about x, the corresponding axial load, that is 0.132 multiplied by 30 divided by 400 by 500. Okay, this gives us a value of 792 kilonewton. Okay, so we have the value of PBY and PBX. Okay, let me write down those values. PBY and PBX. So from that we can find out the value of the K over here. Okay, and before that we need to find out the value of PUZ. Okay, so PUZ is equal to 0.45 FCK into AG plus 0.75 FY minus 0.45 FCK into ASC, which gives me a value of 3448 kilonewton. 3448 kilonewton. Okay. So this particular part where you need to interpolate, you need to be tricky over here. It's a bit tricky. Okay, so you need to be careful. Okay, so if there is any doubt, please feel free to join in the next session so that we can discuss about this. So from this, when we plug the values, so here we have the value of PUZ. Okay, the value of PUZ we have 3448, and the value of PU is 1500 kilonewton, and we can substitute the value of PBX and PBY in order to obtain the values of KX and KY respectively. So the value of KX turns out to be how much? 0.733, and the value of KY turns out to be 0.71. Okay, so it is not at all complicated. Just substitute PUZ as 3448, okay, and PU is 1500. PUZ is again 3448, and PB for X, substitute the value as 792. You obtain the value of KX as 0.733, and for KY, substitute the value of PBY, that is 720. Then we obtain the value of KY as 0.7. Okay, once we have that, we can proceed to solve the problem over here. 0.73 and 0.71. So option C is the correct response. So once we have the modification factor, okay, then we can proceed to find out the the accurate moments, that is MPX, okay, and MTY, that is MUX plus K into MAX, right? And here it is MUY plus K times MAY. Okay, so from this I'm getting the values as how much? So the primary moments are going to remain the same, right? That is 47.5. Okay, 47.5, and this is 54.1, right? No, wait, this is sorry, plus 16, right? So kx is 0.73, 0.71, and we need to, substitute. We need to put the expression for the additional moment capacity, right? That is, we have how much? Here we have 1500 into 10 to the power 3 into 500 divided by 2000 multiplied by 12.75 square, and here we have 0.71 into 1500 into 10 to the power 3 into 400 divided by 2000 multiplied by 15.94 square. Okay, so solving this, we get the value of MPX as how much? 92.92 kilonewton meter, and MTY we are going to get the value as 70.12 kilonewton meter. Okay, these are the design moments. Okay, so as we know, we need to substitute that in this value and find out the expression, right? So we have uh, yeah. So from this we can find out the value of P PU, that is PU by FCK BD, and find out the value of MU. Okay, so MU needs to be found out. Okay, but before that we can find out the value of P by FCK, right? Okay, so we can find out the value of P by FCK. So P by FCK, that is 0.04, right? So this will be 0.25 1500 by 30 by 400 by 500, that is 0.25. Okay, and about x-axis, about y-axis, right? So you can this is 60 by 500, so it is 0 point, sorry, d dash by d, that is 0.12, but on a conservative side you can take it as 0.15. That will give us more conservative value, and here we can take it as 60 divided by 400, that is 0.15 exactly. Okay, corresponding to these two values, you have I get the value of mu x1 as and mu y1 as. Okay, the mu x1 is 255 kilonewton meter, and the mu y1 is 192 kilonewton meter, right? So from here we can proceed to find out the value of, I'll take a different color now just for clarity. So alpha n, as we have already discussed, is a function of pu by puz. Okay, so puz is 0.45 fck. We've already calculated that value. Okay, so from this puz is 3448, right? So pu by puz, that is 1500 by 3448, that gives me a value of 0.43. Correspondingly, alpha n can be, it turns out to be how much? 1.38, because it lies between the value of zero point 0.2 and zero point 0.8. So we can substitute this value, this biaxial moment capacity, that is, what is mux? 92 divided by 255, okay, raised to the power 1.38 plus, what is MUY? MUY is 70.12, right? 70.12 divided by the capacity about Y is 192 raised to the power 1.38, and the biaxial moment demand to the capacity ratio, that turns out to be 0.49. So it is very much less than 1. So this is in conformity with clause 2039.6. So we can say that the column is adequately designed to resist the biaxial moment. Okay. So the correct answer of the biaxial moment demand to capacity ratio as per clause 39.6 is 0.49, and option A is the correct response, and the cross section is safe. So with that, we have come to this end of this rather long session. So to sum up, I can say that this session was the most difficult to explain, and to perform the calculation also in terms of the uh, mathematical rigor that is involved. So I recommend all of you to practice this question, and if there is any doubt, we can always discuss that in the upcoming live sessions. So this is the summary of the two problems that we solved today, two big problems. So the first problem, we basically did the moment interaction curve, right? So we did the moment interaction curve, PM interaction curve. We developed that one, and after that we designed a short RC column under uniaxial load and biaxial bending. Okay, so these are the steps. So this will help you in developing that algorithm or the steps in order to design the short column under axial load and biaxial bending. And these are the series of steps in order to design the RC slender column under axial load and biaxial bending. I suggest and I recommend all of you to go through these steps so that you can solve the assignment problem and the exam problem in a better way. So with that, we have come to the conclusion of today's session. I thank you all, and we'll meet again next class. Okay, thank you.